Taylor series is the subject of today's video lesson, a really interesting and, in my opinion, beautiful area of calculus and complex analysis. Today's video is very straightforward. We're just going to be deriving Taylor series for a given function. In general terms, we'll do specific functions next time. So a Taylor series is, in general, a power series expression for a given function. It's a power series. And in general, power series take the following form. P of x, let's call it, equals some constant c sub 0 plus some new constant c sub 1 times x plus c sub 2 times x squared plus c sub 3, that's also a constant, of course, times x cubed, plus dot, 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 and so on, all the way up to, let's call it c sub n times x to the n. And of course, n can go to infinity. This can be an infinitely long series. The c sub 0 to c sub n are constants, which determine the power series. A Taylor series, though, has a more specific form. And it's said to be centered at some point or some value, a, when we write the series in this form. F of x equals c sub 0 plus c sub 1 times parenthesis x minus a plus c sub 2 times parenthesis x minus a quantity squared plus c sub 3 parenthesis x minus a quantity cubed, and so on. We're essentially translating the series by a. Okay, so in that sense it is centered at a. And the constants are actually what make the Taylor series what it is. The constant coefficients c sub 0, c sub 1, c sub 2 are determined by a formula. And the formula is c sub k, k being any constant, equals fk, or the kth derivative, evaluated at a, all over k factorial. And again, this is the kth derivative, the first derivative, the second derivative, the millionth derivative. That will help us determine our constant coefficient. So c sub 0, for example, equals the 0th derivative. In other words, that just equals the function itself at a over 0 factorial, which would equal f of a, of course. And 0 factorial we know equals 1. So that's just f of a. C sub 0 is just f of a. C sub 1 will be the first derivative of f prime of a over 1 factorial. 1 factorial is just 1, so that's just f prime of a. So c sub 1 is f prime of a. Continuing on the right side here, c sub 2 will equal the second derivative of a, really second derivative of x evaluated at a, over 2 factorial. C sub 3 will equal f triple prime of a over 3 factorial. C sub 4 will equal the fourth derivative. Note that I've introduced some new notation. I'm writing f4 to represent the fourth derivative over 4 factorial. And in general, our nth constant will be fn, the nth derivative at a, over n factorial. So the general form of a Taylor series for a given function, f, centered at a, is as follows. F of x equals f of a plus f prime of a times x minus a plus f double prime of a times x minus a squared all over 2 factorial, which equals 2, plus f triple prime of a times x minus a cubed over 3 factorial, plus the fourth derivative at a times x minus a to the fourth over 4 factorial, plus the fifth derivative of a at x times x minus a to the fifth over 5 factorial, and so on until you get to the nth derivative at a times x minus a to the n over n factorial. And again, we can let n go to infinity. And in the rest of this video, we'll be motivating this definition and showing how it's derived. We're going to show where this series comes from. So let's get underway with our derivation here. So here we go. The derivation of Taylor series. And we begin with the fundamental theorem of calculus. By the fundamental theorem of calculus, we know that if we take the integral of a function's derivative from x to a, so if we integrate from x to a f prime of t dt, that is equal to the antiderivative, so just f of x minus f of a, the antiderivative evaluated at those boundaries, x and a. Therefore, we can rearrange that equation, and we'll get that f of x is equal to f of a plus that integral that we've written, plus the integral from x to a of f prime of t dt. Now, why would we write it that way? Well, what we're going to do now is approximate that integral from x to a of f prime of t dt. So I'm going to approach this at first geometrically. I think doing this visually builds the intuition. So bear with me. I'm going to draw some coordinate axes here. I'm drawing my y-axis and my x-axis. And I'm going to plot a sample function. So that's, I've just labeled them. And ready, poof. There's our function. And it's y equals f prime of x. Now don't be confused by the fact that I'm calling it f prime of x and that in the integral I've written f prime of t. T is just what we term a dummy variable. It has no intrinsic meaning. It gets integrated out when you actually compute the integral. It's just a formality that I'm calling it t. And there are my boundaries from x to a of the integral. And I'm going to put down my y values at those boundaries. So there's f prime of a. And I'm drawing a very thin dotted line across. There's f prime of x on the y-axis. Okay. Now I'm going to draw a little rectangle here, and I'm going to try to approximate the area under this curve with this rectangle. So I'm shading the rectangle in now, just to make it very clear. And we know, again, that this rectangular area approximates our integral. Now, in this example, it underestimates the integral by a little bit. It would be possible to draw the function in such a way that it overestimates. But at any rate, we can assert that the integral from x to a of f prime of t dt is about equal to, within some error, this rectangular area, which is calculated by multiplying the height f prime of a by the length x minus a. Okay? So that's the beginning of an approximation of this area. And we call it a first-order approximation. It involves an expression of x, which is a one-degree polynomial, right? X minus a, not raised to any exponent other than just 1. So again, our first-order approximation is that the integral here from x to a, f prime of t dt, is roughly equal to f prime of a times x minus a. And now I'm going to go a step further. I'm going to see whether we could improve that approximation. And we're going to continue to reason visually here. So I'm redrawing my coordinate axes, and I'm redrawing the function. And this is just a freehand sketch, guys, so bear with me. I'm going to label our boundaries again, a and x. And there's our rectangular region, which approximates the integral to the first order. But now I'm going to go a step further. this additional area that's missing could be bounded by this triangular region. And I know that this drawing isn't perfect, but I'm trying to make that a tangent to the graph. And so that tangent will have the slope f double prime of a, right? The tangent line has the slope is the line whose slope is the derivative of our function. Our function is f prime of x, so the slope at that point will be f double prime of a. The height of this rectangle, the delta y there, is going to be the slope of that tangent line times delta x. Delta y equals slope times delta x. My delta x is just x minus a, the base of the rectangle, or the base of the triangle. So then delta y will equal f double prime of a times x minus a. And the area of this triangular region, which improves the approximation of the area of the integral when added to the area of the rectangle, equals 1/2 base times height. Again, my base is just x minus a. And my height, I just calculated, is x minus a times f double prime of a. So the area of the triangular region is going to equal 1/2 f double prime of a times x minus a times x minus a, 1/2 base times height. Or just f double prime of a times x minus a squared all over 2, or all times 1/2. So my second order approximation for the integral from x to a f prime of t dt, it roughly equals now the area of the rectangular region, f prime of a times x minus a, plus 1/2 f double prime of a times x minus a squared. That's my triangular region. Okay. So far, we have what? We have this integral from x to a f prime of t dt equals f of x minus f of a. That's by the fundamental theorem of calculus. Which equals f prime of a times x minus a. That's our first order approximation, right? That's our rectangular region. Plus f double prime of a times x minus a squared all over 2. That's our second order approximation. That's an approximation using an x squared term. Plus some remainder r. And that remainder needs to be further investigated. And that's what we have so far. So we have a rudimentary Taylor series, the beginning of a Taylor series, which we're writing by rearrangement. F of x equals f of a plus f prime of a times x minus a over 1, plus f double prime of a times x minus a squared over 2. Plus some unknown remainder r. As I said, we're beginning to construct our Taylor series using purely geometric reasoning so far. So as I said, so far we've reasoned geometrically. I've drawn these admittedly shoddy diagrams, but hopefully they get the point across. Now we have to work algebraically, okay? So that's going to involve another level of sophistication here. In our first order approximation, we had the following. The integral from x to a of f prime of t dt is equal to f prime of a times x minus a plus some remainder r. Now part of that remainder had been approximated by the triangular region, which gave us our second order approximation, but here I'm just sticking to the first order approximation to continue to move this argument forward. I'm redrawing our diagram again. Here's f prime of x being graphed. We have our boundaries, we have a rectangular region giving us again the first order approximation, and I'm leaving out the triangular region. So I'm sticking with our first order approximation. I'm showing again the height of the rectangle is f prime of a, the area of the rectangle is f prime of a times the base x minus a. And this remainder r is what's left in the area under the curve. Now let's try to look at that remainder differently and try to express r as an integral itself. I mean, it looks like the bounded area under a curve, so it might be productive to look at it that way. So if our integral from x to a of f prime of t dt can be said to equal f prime of a times x minus a plus some remainder r, then an obvious first step maybe would be to rearrange and write this expression as r equals negative f prime of a times x minus a plus our integral from x to a of f prime of t dt. All I've done is moved f prime of a times x minus a to the other side of that equation and flipped it around. Now I'm going to reintroduce a technique that is hopefully familiar to many of you, which is integration by parts. It's used to perform integrations when we're integrating two functions that are being multiplied together. So I'm going to introduce the functions u and v, and I'm going to let u and v be two different functions for the sake of argument. But they'll be functions of the same variable. They'll be functions of the variable t. And then, by the product rule for derivatives, which we learned early in calculus, and the product rule says, if I have a function which is really the product of two functions, say u and v, multiplied together, if I take that derivative, uv prime equals u prime times v plus v prime times u. In other words, the derivative of the product of two functions equals the derivative of the first function times the second function plus the second function times the derivative of the first. I'm getting a little ahead of myself here, but we can also write this equation. It's going to come back again, so hopefully I won't lose too many people, using equivalent notation d dt of u times v. Remember, u and v are both functions of t, equals u times dv dt plus v times du dt. Okay? That's the product rule. Now, how does that give us integration by parts? Well, first we're going to rearrange this equation. I'm going to get u dv dt equals d dt u times v, the derivative of that product, u times v, with respect to t, minus v du dt. Again, I'm not doing anything fancy here, guys. I'm just rearranging things. And now I'm going to integrate both sides of these equations, of this equation, with respect to t, of course. So if I integrate u times dv dt with respect to t, so u dv dt dt, and then I integrate the other side of this equation, d dt u times v dt minus the integral of v times du dt dt So what happens? Here, the dt's cancel on the left side. Here, integration and differentiation cancel. And in the last term, the dt's cancel again. And I'm left with the expression integral of u dv equals u times v minus the integral of v du. And finally, I can set bounds of integration, which are arbitrary, so I'll call my bounds of integration x and a. So on the left side, the integral has bounds x and a, uv has bounds x and a, and the integral v du has bounds x and a. And this expression is so important that I'm going to put a box around it. We're going to make use of it again and again in the remainder of this video. So what are we going to do with that? We're going to use this identity from integration by parts. And again, that identity is the integral from x to a of u dv equals u times v evaluated at x and then subtracting u times v evaluated at a minus the integral from x to a v du. We're going to use that identity seen in integration by parts to express our remainder, the remainder r, which we saw in our first order approximation, in our first order Taylor series approximation. We're going to use that identity to express r, which again equals negative f prime of a times x minus a plus the integral from x to a f prime of t dt. We're going to use integration by parts to express r as an integral, as one integral expression. So I'm going to unpack this integration by parts a little more. There's our formula. We say let u and v be functions of t, of some variable t. And then, sort of fleshing this out, what that means is that t takes on these two values, x and a, those boundary values. So this expression, integral x to a u dv, equals u of t times v of t. First evaluated at x equals t, and then at a equals t, minus the integral from x to a of v du. So that first term in the expression then is going to be u of x v of x minus u of a v of a, all minus the integral from x to a v du. We're now going to use this expression and work backwards to try to express r as an integral of some form u dv. So we know that r equals minus x minus a times f prime of a plus an integral expression, the integral from x to a of f prime of t dt. And we're going to try to match things up here. The first thing we'll match up is f prime of t with v. Now this is a provisional guess, but we'll see if it makes sense. If we let v equal f prime of t, then when we differentiate, dv dt equals f double prime of t. And that would suggest then that dv would have to equal f double prime of t dt. Now look here, we have a plus sign, and in integration by parts, we have a minus sign. This plus, therefore, must be a double negative. There must be a negative concealed in our integrand. Our integrand contains a factor of negative 1. Now I've already made f prime of t correspond to v, so I'm going to let dt equal negative 1 times du, or equivalently du equals negative 1 times dt. And I'm going to write that into my integrand to make things super clear. So to make this look more like an integration by parts, I've deleted the plus sign and I'm writing minus negative 1 times f prime of t dt. I'm just making it explicit that that integrand must contain a minus sign. Then when we integrate to solve for u, we're integrating du. We're going to get u equals minus t plus some constant c. Remember, this is an indefinite integral, so the constant c still needs to be determined. But we're making progress in setting this up as an integration by parts. I'm going to collect that information on the right side. And now turning to the difference. In our integration by parts, we have a difference. And it looks like we have the second part of a difference here in our expression for r, but we're missing something. So I'm going to write a 0 there. And we're going to see if it's sensible to make that a 0. So again, our f prime of a will correspond to v of a, because we've set v to be equal to f prime of t. And therefore, x minus a has to correspond to u of a. So putting together what we know that u equals minus t plus c. We already found that out. Or equivalently, u equals c minus t. But at the same time, we know that u of a should equal x minus a at t equals a. Comparing those two expressions, it would then suggest that x equals c, or our undetermined constant c must equal x for all of these conditions to hold true. So we can finally write u equals x minus t. And now I'm deleting that 0, and I'm going to plug that in. So I'm going to evaluate x minus t at t equals x, and I get x minus x times f prime of x, which of course just equals 0. The first x is our c, the second x is x equals to t, and that all equals 0. So voila. So let's recap what we just did there, because that was a lot of math. We want to find an integral expression for r, which we know to be equal to negative x minus a times f prime of a plus the integral from x to a of f prime of t dt. Remember, we got this from our first order approximation. And we want to express r as an integral of the form integral u dv, which we know from integration by parts is equal to u times v, evaluated at the boundaries, which here are at x and a, minus the integral from x to a of v du. And we work backwards to figure out u and v. When we do that, we concluded that u must equal, u of t rather, must equal x minus t, and v of t must equal f prime of t. Differentiating then, dv dt is f double prime of t, and dv just equals f double prime of t dt. And now we can plug that into our integration by parts formula. So then we have r equals, again, the integral from x to a of u dv, which means it equals the integral from x to a of x minus t times f double prime of t dt. So that is an exact integral expression for r. I'm going to put a box around that because we're going to make use of this further on. But that's pretty cool. We've perfectly characterized r as its own integral. So, summing up, we began with the following equation: the integral from x to a of f prime of t dt equals f prime of a times x minus a plus some remainder r. And remember, that was our first order approximation. Now we can write, because we found an integral expression for r, the integral from x to a of f prime of t dt equals f prime of a times x minus a plus the integral from x to a of x minus t times f double prime of t dt. But we can go further here because, by the fundamental theorem of calculus, our integral from x to a, f prime of t dt equals f of x minus f of a, which again, just underlining those two expressions, which again equals f prime of a times x minus a plus our integral expression for r, the integral from x to a, of x minus t times f double prime of t dt. Finally, rearranging, we have an approximation for f of x. We can write f of x equals f of a plus f prime of a times x minus a plus this integral from x to a, x minus t, f double prime of t dt. So we're beginning to construct our Taylor series. I'm going to put a box around that. That's an important equation. So now we're going to continue to expand f of x. If f of x equals f of a plus f prime of a times x minus a plus the integral from x to a of x minus t times f double prime of t dt, how can I expand this further? Well, look at this last integral, which I'm going to underline in blue. That integrand is the product of two functions. So again, we can integrate by parts. So we're going to look at the integral from x to a of x minus t times f double prime of t dt. Again, the boundaries are x to a. And I want to express this as, again, a udv type integral. So I'm going to just rearrange this. I'm writing it as f double prime of t times x minus t dt. I've just flipped the product around. Haven't done anything too consequential yet. But I'm going to set f double prime of t equal to u, and I'm going to let x minus t dt be dv. So I just move that up to the top line there. So again, if u equals f double prime of t dt, then differentiating du dt is f triple prime of t, and du is just f triple prime of t dt. Now let's figure out what v must equal. Well, if x minus t dt is said to be equal to dv, we find v by integrating both sides of that equation. So the integral of x minus t dt equals v. So this is a straightforward enough integral. I'm going to do a substitution. I'm going to let w equal x minus t. Then differentiating dw must equal negative dt. dw dt would be negative 1, so dw is negative dt. We're treating x as a constant there. So it becomes the integral of negative w dw equals to v, which equals negative w squared over 2. Subbing back, that equals negative x minus t squared over 2, which again equals v. We just found our v here. So I'm going to now do the integration by parts. This integral equals u times v, evaluated from x to a, minus the integral of v du, again from x to a. So that's going to equal, subbing everything in, f double prime of t times the quantity minus x minus t squared all over 2, evaluated from x to a, I'm running out of room here, minus the integral of minus x minus t squared over 2 times f triple prime of t dt. And those are the bounds of integration. So just moving everything onto one line there, let's do this integration and see what we get. Well, looking at the first term, we're going to get f double prime of x times the quantity negative x minus x quantity squared over 2 minus, now let's evaluate it at a, f double prime of a times the quantity minus x minus a squared over 2. And now here we have a double negative, so that becomes a positive, and it becomes plus the integral from x to a of x minus t squared over 2 times f triple prime of t dt. Well, what happens here? The first term cancels and equals 0. The second term we have a double negative, so that becomes positive f double prime of a times x minus a squared all over 2, plus a new integral, the integral from x to a of x minus t quantity squared over 2 times f triple prime of t dt. So that's pretty cool. Let's recap what we just did. We started with our equation f of x equals f of a plus f prime of a times x minus a plus the integral from x to a of x minus t times f double prime of t dt. Remember, that's our integral expression for the remainder term. And what did we do? We took that integral and we integrated it by parts. And when we did that, we got f of x equals f of a plus f prime of a times x minus a plus f double prime of a times x minus a quantity squared all over 2 plus a new integral from x to a of x minus t quantity squared all over 2 times f triple prime of t dt. So we're now going to take this integral and do another integration by parts. After all, this integrand is the product of two functions. When we do that, we're going to continue to expand our Taylor series. So I'm going to do this integration by parts, but I'm going to move a little faster. So the integral from x to a of x minus t squared over 2 times f triple prime of t dt, we want to set u equal to f triple prime of t, and then we get du equals f quadruple prime of t dt. We'll let our dv be equal to x minus t quantity squared over 2 dt, and then v will equal minus x minus t quantity cubed over 3 times 2. When we plug that in, we then get f triple prime of t times the quantity minus x minus t cubed over 3 times 2, evaluated from x to a, minus the integral from x to a of minus x minus t cubed over 3 times 2 times f quadruple prime of t dt. That's going to equal f triple prime of a times x minus a cubed all over 3 times 2, or 3 factorial, plus the integral from x to a of x minus t cubed over 3 times 2, f quadruple prime of t dt. So hopefully by now you guys are seeing the pattern. We have f of x equals f of a plus f prime of a times x minus a plus f double prime of a times x minus a squared over 2, which is equal to 2 factorial, plus f triple prime of a times x minus a cubed over 3 factorial, we just found that, plus our new integral from x to a of x minus t cubed over 3 times 2 times f quadruple prime of t dt. So we have now a process that we can continue indefinitely. And if we continue the process of integrating our remainder term, integrating by parts the remainder term, we obtain our Taylor series representation for the function f of x centered at a. And we can write f of x equals f of a plus f prime of a times x minus a plus f double prime of a times x minus a quantity squared over 2 factorial plus f triple prime of a times x minus a quantity cubed over 3 factorial plus f quadruple prime of a times x minus a quantity to the fourth over 4 factorial plus the fifth derivative of f at a times x minus a to the fifth over 5 factorial plus, and so on, plus the nth derivative of f at a times x minus a to the power of n over n factorial. Well, thanks for watching. Next time, I'm going to show you guys an alternate, read easier, derivation for Taylor series. Not as elegant in my opinion, but very straightforward. We're then going to prove the important theorem that the Taylor series of a function is unique. Once you've found that Taylor series, that's it. There's no other Taylor series representation for that specific function. We're then going to actually derive some Taylor series. We're going to derive Taylor series for our trigonometric functions sine of x and cosine x, as well as for the exponential function e to the x. And then we're going to prove Euler's formula. Very important formula in mathematics. Thanks. See you soon.